Welcome to this lecture. In this lecture, we will be having a brief overview of what an fuel cell is. So, the introduction to the fuel cell. You're about to embark and journey into the world of fuel cells and electrochemistry. This chapter will act as a roadmap for your travels, setting the stage for the rest of our lectures. In broad terms, this chapter will acquaint you with the fuel cell, what they are, how they work, and what significant advantages and disadvantages they present. From this starting point, the subsequent lectures will lead you onward to your journey as you acquire the fundamental understanding of the fuel cell principles. So, what is basically a fuel cell? You can think of fuel cell as a factory that takes fuel as input and produces electricity as output. Like a factory, a fuel cell will continue to churn up the product, which is the electricity, as long as the raw material, which is the fuel, is supplied. The key difference between a fuel cell and a battery. So this is the key difference between a fuel cell as a battery, that as long as you keep giving the raw materials or the fuel, it will keep on giving you the output, which is the electricity. They both, that is the battery as well as fuel cell, they rely on the principles of electrochemistry to work their magic. A fuel cell is not consumed when it produces electricity, while we see the batteries are consumed while they produce electricity, whereas a fuel cell is not consumed when it produces electricity. It is really a factory, a shell, which transforms the chemical energy stored in a fuel to the electrical energy. So it is basically a shell which transforms the chemical energy stored in a fuel cell to the electrical energy. Viewed this way, combustion engines are also called chemical factories. So the combustion engines, they're also called chemical factories. Combustion engines also take in the chemical energy stored in the fuel and transform it into the mechanical or the electrical energy. So what is the difference between a combustion engine and a fuel cell? What is the difference between a combustion engine and a fuel cell? A combustion engine is called a chemical factory. It also takes in the fuel and transforms it into useful mechanical or the electrical energy. So what is the basic difference between the two? In a conventional combustion engine, fuel is burned, releasing the heat. Consider the simplest example of hydrogen. Like hydrogen, when it is burned in the presence of air, which is oxygen, it will give us water, which is H2O. Then this is a general concept of the hydrogen oxygen fuel cell. So this is your hydrogen and here is your oxygen. You have hydrogen and oxygen. When they both are put or supplied inside a fuel cell, we'll get water and electricity as the products. On the molecular scale, the collisions between hydrogen molecules and the oxygen molecules result in a reaction. So it is the collision between the hydrogen molecules. The hydrogen molecules, they are oxidized, producing the hydrogen molecules when supplied to a fuel cell. When we supply hydrogen and oxygen, they are oxidized and they produce water and releasing the heat, or you can say the electricity. Specifically at the atomic scale, in a matter of picoseconds, hydrogen bonds and the oxygen bonds are broken. These hydrogen, which is HH, and this is your oxygen, which is OO, in a matter of picoseconds, these bonds are broken, while hydrogen oxygen bonds are formed. So these bonds are broken and formed by the transfer of electrons between the molecules. The energy of the product, which is water bonding configuration, is lower than the bonding configuration of the initial hydrogen and oxygen gases. This energy difference is released as heat. So what is this heat which is being released? This is basically the energy difference. Energy difference between the energy of the product water bonding configuration is lower than the bonding configuration of the initial hydrogen and oxygen. So they are at a lower energy, this is at a higher energy. So the energy difference is released as heat. Although the energy difference between the initial and the final states occur by reconfiguration of the electrons as they move from one bonding state to another, this energy is recoverable only as heat because the bonding reconfiguration occurs in picoseconds and at an intimate subatomic level. To produce electricity, this heat energy must be converted into mechanical energy. Then this mechanical energy must be converted to the electrical energy. Now we are getting heat when we have hydrogen and oxygen. When they give water, it is giving heat. Now the thing we need to do is we need to convert this heat to mechanical energy, and this mechanical energy needs to be converted to your electricity or your electrical energy. Going through these steps is potentially complex and inefficient. So consider an alternative solution to produce electricity directly from the chemical reaction by somehow harnessing the electrons as they move from the high energy reactant bonds and to the low energy bonds. In fact, this is exactly what a fuel cell does. But the question is, how do we harness the electrons that reconfigure in picoseconds at subatomic scales? The answer to this spatially separate the hydrogen and oxygen reactants so that the electron transfer necessary to complete the bonding reconfiguration occurs over a greatly extended length, and then the electrons move from the fuel species to the oxidant species, and they can be harnessed to an electrical current. So, so this is a schematic diagram of the hydrogen oxygen combustion reaction. So these arrows here are indicating the relative motion of the molecules participating in the reaction. Starting with the reactants here, H2O2, these are gases, right? So you have hydrogen atoms, hydrogen molecules, and you have oxygen molecules. When they both react, okay, they both must be broken first, requiring an energy input before hydrogen oxygen bonds are formed, leading to the energy output. First energy input needs to be done to break, then when they both react, then energy output will be given. Okay, so this is your now understanding this bonds and energies in a little more deeper method, which is atoms are social creatures. So what are atoms? Atoms are social creatures. They almost prefer to be together instead of alone. When atoms come together, they form bonds, lowering their energy, shows a typical energy distance curve for hydrogen-hydrogen bond. When the hydrogen atoms are far apart from one another, no bond exists and system has a high energy. As the hydrogen atoms approach one another, the system energy is lowered until the most stable bonding configuration is reached. Further overlap between the atoms is energetically unfavorable because of the repulsive forces between the nuclei begin to dominate. Remember, energy is released when the bond is formed and the energy is absorbed when the bond is broken. Energy is released when it is formed and it is absorbed when it is broken. It is released when a bond is formed. Here, bond is forming. So energy is released because it is more stable. It is at stable means it is at a low energy. Here it has a high energy, but the stability is less. Okay, for a reaction to result in a net release of energy, the energy released by formation of the product bonds must be more than the energy absorbed to break the reactant bonds. So the energy required to break, or the which needs to be supplied to break the reactant bond should be less than the energy released when the bond is formed in the chemical reaction. So that is what leads to the stability. So understanding a simple fuel cell, in a fuel cell, the hydrogen combustion reactions is split into two electrochemical half reactions. Now we clearly know why these electrochemical half reactions we do. What is the reason for the half reaction? Because if they are done in a matter of picoseconds, the bonds break and new bonds are formed. So we do not have that time to store or harness those electrons. By having the half cell reactions, we can harness those electrons and convert them into the electrical energy. So these are the two half cell reactions. We have one hydrogen which is getting broken into the proton and giving out two electrons, and this oxygen atoms, they are taking when they combine with the hydrogen proton and they take in the two electrons, they form water. So these are your two half cell reactions. So by spatially separating these reactions, the electrons transformed from the fuel are forced to flow through an external circuit, thus constituting an electric current and do some useful work before they can complete the reaction. Spatial separation is accomplished by employing an electrolyte. Now, how do we spatially separate these? Now, how do we spatially separate these two reactions? They are employed by using an electrolyte. Now, what is an electrolyte? It is a material that allows ions, which are charged atoms, to flow. Electrolytes, they basically they allow the species such as charged ions to flow, but not electrons. So this is the definition of an electrolyte. It is a material that allows ions or charged atoms to flow, but not electrons. So at a minimum, fuel cell must possess two electrodes, where the two electrochemical half reactions occur separated by an electrolyte. So we have that a fuel cell must possess two electrodes, where the two electrochemical half reactions occur separated by an electrolyte. So figure 1.4 shows, so this is figure 1.4, this shows a simple fuel cell. Example of an extremely simple hydrogen oxygen fuel cell. This fuel cell consists of two platinum electrodes dipped in sulfuric acid, which is an aqueous acid electrolyte. Hydrogen gas bubbled across the left electrode. This is your left electrode, and hydrogen gas is bubbled across this electrode and is split into the protons, which is H plus, and electrons. Following equation discussed above. The protons can flow through the electrolyte, that is the sulfuric acid is like a the C of H plus, but the electrons cannot. Instead, the electrons flow from left to right through a piece of wire that connects the two platinum electrodes. Note that the resulting current, as it is traditionally defined, is in the opposite direction. When the electrons reach the right electrode, they recombine with the protons and bubbling oxygen gas to produce water. Following equation 1.3, if the load, that is a light bulb, is introduced along the path of the electrons, the flowing electrons will provide power to the load, causing the light bulb to glow. Our fuel cell is producing electricity. The first fuel cell invented by William Grove in 1839 probably looked a lot like the one discussed here. So this is a very simple fuel cell. You have these two electrodes, platinum electrodes, and your sulfuric acid electrolyte. When the hydrogen gas is bubbled, H plus ions are produced and your electrons are produced. So because when hydrogen is split, it gives us H plus ions and electrons. Okay. So this electrolyte is like a C of H plus. So when this H plus, like you have this oxygen here, right? So you have oxygen, and when this combines with this H plus coming from here, it gives out the water, and the electrons traveling can give us the electricity. So the thing to be discussed here is that your energy, power, energy density, and power density. Now, to understand how a fuel cell compares to a combustion engine or a battery, several quantitative merits or figures of merits are required. The most common figure of merit is used to compare energy conversion systems. They are power density and your energy density. To understand energy density and power density, you first need to understand the difference between energy and power. Now, what is energy? Energy is the ability to do work. It is measured in joules or calories. Power is defined as the rate at which energy is expended or produced. In other words, power is the intensity of the energy use or production. Power is a rate. The typical unit of power is watt, and it represents the amount of energy used or produced per second. From the above discussion, it is obvious that the energy is a product of power into time. So although the International System of Units has the SI unit uses the joule as the unit of energy, you will often see energy expressed in terms of watt, hour, or kilowatt. These units arise when the units of power, example watts, are multiplied by the length of time, example hours. Obviously, watt hour can be converted to joules or vice versa. So this is your simple calculation. So what is now, so we have for portable fuel cells and other mobile energy conversion devices, Power density and energy density are more important than power and energy because they provide information how big a system needs to be to deliver a certain amount of energy or power. Power density refers to the amount of power that can be produced by a device per unit mass or volume. So this is what power density is. Power density refers to the amount of power that can be produced by a device per unit mass or volume, and the energy density refers to the total energy capacity available to the system per unit mass or volume. I repeat these again. Power density refers to the amount of power that can be produced by a device per unit mass or volume, and energy density refers to total energy capacity available in the system per unit mass or volume. So this is produced. This is the total energy capacity. Volumetric power density is the amount of power that can be supplied by a device per unit volume. And gravimetric power density is the amount of power that can be supplied by the device per unit mass. So that is per unit volume, this is per unit mass. Then you have volumetric energy density is the amount of energy that is available to a device per unit volume, and gravimetric energy density is the amount of energy that is available to a device per unit mass. So we finish this lecture here, and the subsequent lectures will be following the advantages and disadvantages of our fuel cell.